Alright, we finally figured out all of our OBS issues. We've got the audio working. I tested out the camera. The camera is indeed working. And we are ready to finally get into Chapter 5 of Computer Organization and Design, where we finally get to talk about one of the most important parts of the processor, which is going to be, of course, the memory hierarchy. It's one of our biggest bottlenecks, and it's one of our absolutely most crucial parts of the processor. And it enables so much, and honestly, it hasn't gotten much better over time. You know, capacity has gotten better, but let's not talk about latency. Latency is another issue. Maybe we'll get some better memory soon. High bandwidth memory is pretty good. HBM2, as on the Volta card. But hey, that's not why we're here. We're here because we're going to have some fun. And also, we have a lovely new addition today, is that we have a camera today. So hi guys, how's it going? I'm Nick from Engineering Today. We got a discount camera. It's a Logitech, what is it? 920 or something? I got the box here someplace. We have a Logitech C920. Very nice. This is the lab. It's our humble lab. It's not too special. Most computer engineering labs aren't that special, to be honest. What can you really show off in a computer engineering lab? They usually just have desks and they have monitors. So, you know, we might do a desk, a tour of the desk. You can see my Shakeology bottle. You can see my jar of peanut butter, my hand vac. It's cheap, I got it from Amazon. But guess what? We're gonna have a lovely day today. Oops. And we'll start out with our theme song. Alright, we've got a new setup, finally. Okay, so what have we gone over recently? So we went over the first week, we introduced what a computer was, or a processor was, and some foundational ideas for how to design a computer. What did we do week 2? Week 2, we introduced the instruction set. Very important. If we're going to work on a processor, we should understand the instruction set. So typically the architecture of a computer boils down to two things. It boils down to the microarchitecture and then the instruction set architecture. So the instruction set architecture works on the microarchitecture. Those two things combined make up the architecture. So when we say microarchitecture, we're talking about the individual components. When we talk about instruction set architecture, that's what instructions are supported on that hardware. Chapter 3. What did we do chapter 3? That was arithmetic, so we had to figure out what we were doing. We had to figure out what we were actually doing on our machines. Hardware has to execute some arithmetic operations, be they logical operators or arithmetic operations. Even things like branches are essentially arithmetic operations. We take the program counter, we increment it by some value or decrement it by some value. That's the nuts and bolts of what we do is addition, subtraction, multiplication, and division. More so addition and subtraction, and then some of the logical operators like and or. For when we're doing things like comparison, or no. Comparisons are done by subtraction. So I would say subtraction and addition are probably the two key operations that we actually do. So what did we do? Chapter 4? Oh, that's right. Chapter 4 we did the, it was our first time looking at the CPU. So it was the control path and the data path, and we introduced, okay, what does a single cycle processor look like? And we also looked at what does a multi-cycle processor look like. A multi-cycle in this case, we jumped ahead from multi-cycle all the way to pipeline. It doesn't make much sense to look at just a regular multi-cycle processor because a pipeline is just it's a small extension from, it's just a small extension away to get to a pipeline from a multi-cycle. You basically just you more clearly define the stages, and then you make those stages be able to hold some value, so some forwarding information, some bypassing information, and you've got to play around with the control a little bit. And it's really useful for us. But now we're on to probably one of the most difficult parts of computer architecture, which is generally the memory hierarchy. The memory hierarchy itself, the hardware, it doesn't have to be terribly complex, but managing it is what the real difficulty is. Once we get into things like multi-core, multi-core is the real problem, because once we get to multi-core, we start having multiple threads. Yeah, we got the face cam now. Welcome to the stream. Welcome to the lab. This is the architecture lab at my university, or it's one of the architecture labs. There's more than one professor that does architecture, but this is the one that I work in. So welcome. We're gonna have a nice day today. So the key point is that memory, the structures are fairly simple. Don't tell a VLSI person that actually has to implement them. Don't tell them that it's really simple. However, from the outside looking in, if we were to abstract it, the hardware is pretty simple. The key point is that managing it can be difficult. So how do we make sure that when we're storing information into this memory hierarchy, we're doing it efficiently? We're not having things happen like thrashing, where we're trying to write too much information into such a small space that we can't exploit any temporal or spatial locality. And then once we get to something like multi-core, which we won't really get into in this book, but it's a more advanced concept that we'll reserve for. Where's the book? Ah, here it is. So I actually have two of these books. So here's the book we're going through now. I have the MIPS version. Ta-da! Computer Organization and Design. This is the MIPS one. We're going through the RISC one, but the books are essentially the same. This is the heavy hitter book right here. This is Computer Architecture, a Quantitative Approach. This is what every single graduate architecture program uses as a book. So we'll go ahead and we'll go through that sometime. We'll get more into multi-core in that book. That book focuses on modern processors. The appendix in that book is pretty much just chapters on reviewing this book. So let's get started. Let me make sure the tablet's working. Sometimes I have some problems with these things. It's not terribly fun. Namely because so I'm on Linux, like you guys know. But the problem when you're on Linux with this thing is that can you guys see the text okay, or should I make the camera smaller? I can make the camera smaller and I can zoom in some. I'm still playing around with the features. Let me see what this looks like full screen on my monitor. Looks okay. We can leave it this size if you guys want. Seems fine? Okay. Well, that's perfect then. Okay, large and fast. So we want to give the impression that we have a very large memory structure, but then we also want to get the idea that we have a fast memory structure. So we're going to describe how we get that through what we call the memory hierarchy, and how it exploits locality to give this impression, even though we have a more triangular shape to the memory hierarchy. So using this idea of locality, we can get over some of the bad things with long latencies of memory accesses, especially to disk. Disk is awful. The chapter concludes by emphasizing the memory systems are a central design issue for parallel processors, and that the growing importance of the memory hierarchy in determining system performance means this area will continue to be the focus of both designers and researchers for years to come, especially because it's so slow. So there's 1,000 different terms that we don't need to look over. Let's see, what is it? This is from the classic paper. Ideally, one would desire an indefinitely large memory capacity such that any particular word would be immediately available. We are forced to recognize the possibility of constructing a hierarchy of memories, each of which has a greater capacity than the preceding, but which is less quickly accessible. So, even back in 1946, we have the idea of a memory hierarchy. So isn't that crazy? This is something that we still work on today. And back in 1946, it was introduced. So a senior level class in architecture, you're learning about something that was proposed in 1946. So don't get an impression that what you learn in undergrad is what happens in the real world. So what are we going to talk about? So a brief introduction followed by the memory technologies. So probably going over DRAM and SRAM, two of the more common designs for things like caches in memory. The basics of caches. So what is a cache? Why do we need them? Why do we care about them? Measuring and improving cache performance. So just because we have a cache doesn't mean we can't make a cache better. We'll see things like associativity and how that can affect our performance. Then we have the dependable memory hierarchy. So probably a brief section on some fault tolerance. Then we'll talk about virtual machines and virtual memory. Virtual memory is a very important concept. A common framework for memory hierarchy, so probably some implementation. So how do we control a simple cache using something like a finite state machine? Then we'll briefly touch on some more advanced stuff, so specifically parallelism in the memory hierarchy. So how do we deal with things like cache coherence? It talks a little bit about RAID, which stands for redundant array of inexpensive disks. Typically, I learned this as redundant arrays of independent disks, not inexpensive. If you look at RAID doesn't have to be on inexpensive disks. You can have RAID with $10,000 to $15,000 PCIe SSDs. So probably better known as independent disks. Let's see, is this where you go for the comp sci Jordan Peterson forum? Wowee. No, this is where we go for the computer architecture, engineering today, learn with Nick time. Your camera has some delay, I believe. Yeah, I'm still trying to work out the bugs with it. A lot of it probably has to do with the fact that the Linux port of OBS is really, it's something. Looking good for today's stream. Yeah, I try to look good. This is typical office wear for me, or lab wear. Luckily, I don't need any. I don't need any glasses, like safety glasses. So, maybe a brief bit on implementing cache controllers if we have time, but we're mainly going to skip over a lot of this. This implementation type stuff. We don't need to go over something like Verilog or VHDL or whatever they do. And then specifically we'll look at, of course, pitfalls and fallacies and pitfalls. It's always important for us, isn't it? Okay. So let's begin. So as we all know, last time we looked at this control and data path. We haven't gone over input and output yet. But we have a general idea of how a computer is formed from the first couple chapters. But now we're on to one of the most important things, which is memory. All right, introduction. So from the earliest days of computing, programmers have wanted unlimited amounts of fast memory. And so we saw that from that quote from the... we saw that from the John von Neumann paper from 1940. It was the first draft of it was actually 1945. So at least since 1945, this has been an idea. So before we look at creating this illusion, consider the simple analogy that illustrates the key principles and mechanisms that we use. So suppose you were a student writing a term paper on important historical developments in computer hardware. Who's this cutie? Hey, it's your friend Nick from Engineering Today. My camera right now is being held down by a jar of Jif Extra Crunchy peanut butter with 7 grams of protein per serving. Maybe we'll show that near the end of the stream. I'll have to figure out a way to mount the camera on my shoulder so we can do some cooking streams with it, and I can just plug it into my laptop or something. Okay, so suppose you're writing a term paper on historical developments in computer hardware. The man, the myth, the legend. Yeah, it's me. It's Nick from Engineering Today. I'm glad that you're all here today. Thanks for joining me. You find a book on early British computers that covers EDSAC. So EDVAC is typically the one that we care about. But this time we're talking about EDSAC, which is a precursor. Let me move this over so I can see chat better. Okay. So once you have a good selection of books on the desk, so you're trying to learn more about something, so you put a bunch of books on the desk in front of you. There's a high probability that many of the topics you need can be found in them. So you have a bunch of books on the desk, and there's a likelihood that within some of those books, there's information on, say, this computer that you want to look up. And you spend most of your time just using the books on your desk without returning them to the shelves. So having several books on the desk in front of you saves time, compared to having only one book and constantly having to go back to the shelves, return it, and take out another. So we're getting this idea of locality. So instead of every single time we want to, pull some information or find some information, instead of having to, go run up and down the shelves, as we use data, we can just, put it on the table in front of us, and there's a good chance that we're going to have to re-access that data at some point, typically pretty soon, and that's this idea of temporal locality. And it's oftentimes likely that, say, if we went to the library shelves and we looked at books on computer architecture, well, it's likely that where that is in the library, there's going to be a lot of books on computer architecture near each other. So we're talking about the principle of locality here, which is generally broken up into two kinds, which is temporal and spatial locality. So temporal means we're talking about locality within time. So if an item is referenced, it will tend to be referenced again soon. So if you want an example of temporal locality, take the case of say assignment, right? So you say int a is equal to 5. Okay, well, you just assign, the variable a, the integer variable a, the value of 5. Now, if you're writing a program, it's probably pretty likely that the next instruction, you're probably going to be doing something with that value a. So, we can make some good guesses about these things, and we can, look through the program and say, okay, we've got some locality here. We're going to be reusing this variable. And then we have spatial locality, locality within space. So if an item is referenced, items whose addresses are close by will tend to be referenced soon. So in this case, consider something like an array. So if we're doing a bunch of reads from an array, say we're doing a bunch of print statements, and so we're printing everything from an array. So if we look at index 0 first, well, it's probably pretty likely that the next thing we're going to address is index 1, then index 2, then index 3. So we've got some spatial locality there. And we'll see how both of these things, we'll see how memory hierarchies use things like spatial locality and temporal locality, and how that's really the foundation of their design. So those are the ideas that we just went over. And so we'll take advantage of both of these, the principle of locality, by implementing a memory of a computer as a memory hierarchy. A memory hierarchy consists of multiple levels of memory with different speeds and sizes. Engineering Today, Pixel Shroom would like to be unbanned. He says he needs to learn more for his courses. Sure, I can unban Pixel Shroom. I didn't actually even, let's see. Let's go to moderation on this screen. Is it under moderation? No. Channel. Listen, if he can tell me how to unban him, I'm more than happy to unban him. Let's see. I assumed it would be under moderation. So it's not there. Let's see if it's under channel. Let's see. Streaming, no, it's not going to be under there. Listen, if Pixel Shroom can tell me how to unban him, I'd be happy to. Until then, he's banned. Is it someplace on the dashboard page? Also, it refreshes my chat, so if you already typed me the answer, you're probably going to need to type it again. Try in chat. Oh, probably. What the heck is his, let's see. 1232? Okay. / unban Pixel Shroom 1232. Okay, Pixel Shroom's unbanned now. We got it. We fixed it. Okay. Pixel Shroom can come learn. If he posts one more not safe for work link, he's permanently banned with no recourse. Okay, so we talked about the memory hierarchy. I live, I die, I live again. There you go. Good man. Lev, you guys gotta calm it down a little bit. We have to. We're an accepting, we're a happy, we're a go-lucky chat. So what do we got? So like we said, we're going to create this illusion that we have a very large memory system that's very fast using the idea of a memory hierarchy. So we have these cascading levels of memory of different sizes made out of, oftentimes different technologies. So this is the general structure of the memory hierarchy. So at the very fastest and closest to the processor, we have, this is the cache is generally the L1 cache, and then even the L2 cache sometimes can be SRAM, depending on the architecture. So SRAM it's a lot faster, but it's a lot more expensive, and that's because DRAM is made from a capacitor and a single transistor, and even the capacitor. So we're not talking about like a discrete capacitor. We're talking about a capacitor that's fabricated based upon the inherent capacitance of the what is it called? The trace. So the trace between two different things. So you can think of a trace as a wire, but it's embedded into like the silicon. So the capacitance is actually just based on the trace and the trace width. So the capacitor doesn't exist as a physical component there. So with SRAM that we have, I believe it's 4 transistors and 2 capacitors, or maybe 4 transistors and 4 capacitors. But basically we're saying we're basically times 4 what we need for DRAM, we need for SRAM, but it's a lot faster. Then for DRAM, that's generally next. So maybe the L3 cache, and then of course main memory is going to be DRAM. And then, a lot of times today we've got some better stuff when it comes to our disk, but disk still is pretty darn slow. But we get a really big size from the disk. And so this is going under the assumption of a magnetic disk, because a lot of people still use magnetic disks. And if we look at something like servers still use magnetic disks. They don't use SATA drives generally. They use something called SAS drives, which stands for Serial Attached SCSI. And then SCSI stands for Small Computer Systems Interface. SCSI. But yeah, so magnetic disk is still pretty common, especially in the server realm. So the data are similarly hierarchical. The closer to the processor is generally a subset of any level farther away, and there's even things we can do to ensure that everything in the L1 is a subset of what's in the L2. Everything in the L2 is a subset of what's in the L3. Everything in the L3 is a subset of what's in main memory. So we can make that guarantee as well, but that's not always the case. So a memory hierarchy can consist of multiple levels, but data are copied between only 2 adjacent levels at a time. So we're not, if we need to write something to disk, we're not going, okay, we're at the L1, let's just bypass everything and go to disk. No, the L1 has to go to the L2, L2 has to go to the L3 or main memory, and then main memory has to go to disk. So the upper level, or one closest to the processor, is smaller and faster. So like we said, generally made out of something like SRAM. So let's go on. Okay. So figure 5.2 shows that the minimum unit of information that can be either present or not present in the 2-level hierarchy is called a block or line. In our library analogy, a block of information is one book. So if we're in a library and we're considering books are the data that we're talking about, we can't just go to the shelf in a library and then tear out a page of the book and bring it to the table we're working at. We have to either take the book or we have to put the book back. We can't take a page from the book and put the page back. So there is a minimum granularity that we can work out. Okay. And then things like the block size or the cache line size, those can vary between processors. Okay. Let's see. So if the data requested by the processor in some block in the upper level, so if it's in that level, it's called a hit. So this is the same thing as if we had a book on our table and we found the information that we wanted in that book. That would be analogous to a cache hit. And then we have something like hit rate, where the hit rate or hit ratio is the percentage or the fraction of time that we find the information we're looking for when we try to access it. So it's basically we have some information in our cache, we have a book on our table, and we find the information we're looking for within that book. We find the data we're looking for in that cache. Is it me, or is there some desync with the audio and the video? There might be. There very likely is. I haven't finely tuned this very much. We can, listen, we'll fix that soon. Like I said, it's really hard to correct things because this is the port of OBS for Linux, and there's a lot of things that don't work with it. Like all the Streamlabs stuff. The Streamlabs stuff doesn't work with it. I have to launch it and do window capture and then crop it. I can't just launch it. All right. So, since performance is a major reason for having memory hierarchy, the time to service hits and misses is important. So hit time is the time it takes to access the upper level of the memory hierarchy. So it's the time needed to know, okay, is it a hit or miss? And then the time to actually get that data from memory. So that's our hit time. And then we have our miss penalty, which is the time that it takes to replace a block in the upper level. So like we said, we can't just copy something from the disk to, say, the processor directly. The disk has to go through the memory hierarchy. Because the upper level is smaller and built using faster memory parts, so usually SRAM, the hit time will be much smaller than the time to access the next level. So if we hit in the L2, it's a lot faster than if we miss in the L1. Or sorry, if we hit in the L1, it's a lot faster than if we miss in the L1 and hit in the L2. And it's a reason why we design it this way, where it cascades outward, because it gets worse and worse. And by the time we're getting to disk, we're talking about tens of thousands or hundreds of thousands of clock cycles to get back. Windows Server 2012 time? For what? Oh, for to use the Windows version of OBS. No, listen. Here's how we get the perfect stream, right? Besides me iterating and playing with settings on OBS forever to patch it to make it work. We build a streaming PC. But that requires money, and I don't have that because I'm a grad student. Okay, so we went over hit time and miss penalty. So what's the big picture? So programs exhibit both temporal locality, which is the tendency to reuse recently accessed data items, and spatial locality, the tendency to reference data items that are close to recently accessed items. So let's go over what this means. So when we talk about, let's use red. So when we talk about something like temporal, this is the idea that we do something like int a, and then, or let's say int a equals 5. And then immediately after it, we might do, a equals a plus 5, right? So this is the idea of temporal locality. If we use something, it's likely that if we say initialize something, it's probably pretty likely that we're going to use it soon. So, and then when we get to the idea of spatial locality, we can think of the idea of an array. So for spatial, you can think of, if we're accessing an array, 0. Well, it's likely that the next thing we're going to do is probably access the next element in the array. So spatial and temporal locality, that's what we're trying to take advantage of. So memory hierarchies take advantage of temporal locality by keeping more recently accessed data items closer to the processor. So if we initialize something like A, it's likely that A will be stored in the L1, and when we use A again, we'll probably hit it in the L1. So memory hierarchies take advantage of spatial locality by moving blocks consisting of multiple contiguous words in memory to upper levels of the hierarchy. So if we access, say, A0, well, it's likely that we're going to design a system where it brings A0, A1, A2, A3, A4, and so on into the L1 cache. That way, face cam. Whoa, yeah, we got a face cam today. Hi, everyone. It's nice to see you today. Okay. And so this is what we mean by that hierarchy. So smaller and faster at the top, larger capacity, but we take a hit on performance at the bottom. So let's look at memory technologies. It's important that we understand what we're working with. That way we have, when I say SRAM, when I say DRAM, or flash, or, the magnetic disk, what are we talking about then? So, like we said, the four main technologies are Main memory is going to be in DRAM, or dynamic random access memory, while the closer levels, so the caches, use SRAM, which stands for static random access memory. So DRAM is less costly per bit because it's a single transistor and a capacitor versus 4 transistors and 4 capacitors, or whatever modern SRAMs are made from. It's cross-coupled inverters, and inverters are 2 transistors each. So it's minimum 4 times bigger. However, if you think about it capacity-wise, if you have only 1 transistor per bit, you're going to get 4 times the capacity if you use DRAM instead, because instead of 4 transistors, you have a single transistor. So it's cheaper for a larger capacity. So the price difference arises because DRAM uses less area per bit of memory, so we went over that. So the next technology besides flash and DRAM, besides DRAM and SRAM, is going to be flash. So it's non-volatile, so the first 2 are volatile, and is the secondary memory in PMDs, or personal mobile devices. And then the largest but slowest level in the hierarchy in servers is your good old magnetic disk. So, depending on what technology you're using for magnetic disk, it's going to determine how fast it's going to come back. And so here we can see some of the, what we're talking about as far as scaling. So per gig, SRAM is going to cost $500 to $1,000. So when we're talking about, the size of, a cache, that's why we're generally talking in terms of, kilobyte, or maybe megabyte. We're not talking in terms of gigabytes of SRAM. The next thing, DRAM, so what we make main memory from, $10 to $20 per gig, pretty good. Also notice that when we're talking about SRAM latency or access times, we're in the sub-nanosecond range. So 500 picoseconds to around 2.5 nanoseconds. Oh, did we get my first donation ever? Zlatenbest. Thanks for the $3, man. I really appreciate it. You're helping make this stream great. That is going to go directly to buying a cup of coffee, because I'm probably not going to get out of this lab until around midnight tonight. Listen, Zlatan, you're going to go down in history. You're the first donator to this stream. Lev was the first person to donate bits. ABD7 was the first person to be a Twitch Prime sub. We've got a lot of firsts. And then, I forgot who the first person to subscribe was, not using Twitch Prime. We'll figure it out. We'll make a list. You guys are going to be, just know that you're near and dear to my heart. So notice that once we get from SRAM to DRAM, we go from the sub-nanosecond range of timing to 50 to 70 nanoseconds. So we're talking, orders of magnitude increases in access time. Now we're still in the nanosecond range, which it's pretty good. It's not bad, but it's not great. It's not great. So then we move on to flash, and so we go, okay, well, flash is non-volatile. It's used in smartphones. We see that we get a little better in our per gig as of 2012. Now, it's going to get a little cheaper and a little faster as technology increases, but the trends stay the same. So 0.75 to $1 per gig, that's pretty good. Well, it's no wonder flash drives are so cheap now. But look at that access time. We're talking about 5K to 50K nanoseconds just to access it. We're pretty far from that 500 picosecond access time of SRAM. And then we get to magnetic disk, and if you ever wondered why it was so awful back in the day when you had a magnetic disk and you can never go back now that you have a a solid state drive. It's because it takes 5 million to 20 million nanoseconds to access a magnetic disk. It's it's a joke. So there's actually a very interesting thing where it's something called RDMA. It's remote direct memory access. And there's these really cool machines. I think IBM's done a lot of work on them. And so the way it works is you have pooled resources of memory. So like your caches and your memory hierarchy is located not on your machine. It's on a machine it's out there someplace. But you're connected over RDMA. And so what happens is you access, so when you want to access the memory hierarchy, you will send a request over RDMA to a remote machine. You'll go through the memory hierarchy on a remote machine, with a larger pooled cache and a larger pooled memory hierarchy. And the funny thing is, the access time to go over RDMA, to go into the memory hierarchy on a remote machine, transfer that information back from the remote machine, is faster than going to disk on your own PC. So it's faster than the 5 million to 20 million cycles to just go to your own disk. So there's some really cool things like that. So that's why the memory hierarchy is important, guys. Stay in school, learn about your memory hierarchies. So let's talk about SRAM. Static random access memory. They're simply integrated circuits that are memory arrays with a single access port that can provide either a read or a write. They have a fixed access time to any datum, though the read and write access times may differ. So we'll notice that we can't make the analogy of something like a door. So with a door, it's generally the same. It takes the same amount of effort to open and close a door, but with caches, it's a little bit different. Reads and writes can take different amounts of time, and we're not going to go into why that is in this class, but maybe in the integrated circuits one that we're going to do later, we'll get into that. So unlike DRAMs, SRAMs don't need to refresh, and so the access time is very close to the cycle time. So SRAMs typically use 6 to 8 transistors per bit to prevent the information from being disturbed when read. SRAM needs only minimal power to retain the charge in standby mode. So that's this idea why we don't need a refresh. It's because they use so little power compared to something like DRAM. So in the past, most PCs and servers use a separate SRAM chips for either their primary, secondary, or tertiary caches. Today, Moore's Law, all levels of caches are integrated onto the processor chip. So Moore's Law, remember, it says that we're going to get twice, every 2 years, we get twice of the amount of transistors in the same area. So transistor size shrinks by half. So we can just fit everything on chip now, which is great. But, Moore's Law is kind of dead. Uncle Moore died. Uncle Moore, in his trust fund, it ran out. It ran out. Now, don't say Gordon Moore died. Gordon Moore is still very much alive. One of the founders of Intel. Okay, so let's talk about DRAM now. So in SRAM, as long as power is applied, the value can be kept indefinitely. But in dynamic RAM, we need that refresh like we were talking about. The value is kept in a cell and stored as a charge in a capacitor. Now, capacitors leak. They're not perfect, so that's why we need to refresh it. And then a single transistor is then used to access this stored charge. So either to read or to overwrite the charge stored there. Okay. So because they're only using one transistor versus 6 or 8, it's a lot denser, so we can fit a lot more storage into the same space that we could with DRAM. Okay. So as DRAM store the charge as a capacitor, it can't be kept indefinitely. Okay, so it's talking about the idea of refresh. So to refresh a cell, we merely read its contents and write it back. Seems pretty bad, right? Every once in a while, we just have to periodically refresh all of the DRAM. Now, we generally, meter this out, and we do some monitoring to see which rows we need to refresh when. But, it's very dependent on your access patterns, right? So if you're making a lot of access patterns and there's a lot of cross-coupling, you're probably going to need to refresh adjacent rows. So this is not something where you just go down the line of row 1, 2, 3, 4, 5, 6, 7. It's something where it depends on how you're accessing. So how caches are designed, or how DRAM cells are designed, we'll leave that. I leave that as an exercise to the viewer. We may talk about that on another stream, though. Okay. So like we said, all we really need to know is that when we need to do a refresh, we have to read the contents, write it back to the same spot. Okay. So this shows a little bit of how modern DRAMs work. So they're organized in banks, typically 4 for DDR3. Each bank consists of rows sending a pre-charge command, opens or closes a bank. A row address is sent with an activate, which causes the row to transfer to a buffer. When the row is in the buffer, it can be transferred to successive column addresses at whatever the width of the DRAM is, typically 4, 8, or 16 bits, or by specifying a block transfer and a start address. Each command, as well as the block transfers, is synchronized with the clock. So the way this works is we have to send an activate, and we have to say, which bank are we going to be reading from, where are we going to be reading from, and then that's going to be done with a pre-charge, so we can first activate the bank, and then we need to access said bank. So we activate it. So here we can see the idea of Moore's law again. So 1980 with DRAM, we're talking about per gigabyte $1.5 million. So if you ever wondered why it was, why we had such small values back in the day of say DRAM and stuff, it's because the cost per gig was like $1.5 million. Now, 2012, we're down to $1. And we see that the access time has also gone down considerably. So we went from 250 nanoseconds back in the 80s. So this was around the time, so 1980, 1985, this was around the time where CPUs started to get things like precise state and reorder buffers. And then we see that by today, we're down to like 35 nanoseconds. And then the column access time. So the 35 nanoseconds is to access the row, but then to access a column to an existing row, something that we've already tried to access, we're down to 0.8 nanoseconds now. So pretty good. We're doing pretty well. Slotin, I'm sorry that it didn't show up on the donations for a cup of coffee tracker. I'm not sure why that's not updating. Oh, it's probably because it went out. The deadline for the goal. Let's see. Let me see if I can. Oh no, it says. Huh. Let's look at settings real quick. Oh, it's probably filled in. So bar color, bar background color. Real human being is now following. Hey, thanks for following, man. Let's see what happens if I change it to red. Let's see if it updates on the stream. Did it update? Nope. That's okay. Oh, maybe I didn't save the settings. Oh well. That's okay. I know it showed up, but it didn't show up on the bar down here. Okay, so let's move on. So we talked about, we can just get rid of the, let's get rid of that if it's not going to update. That way we get a little more space on the screen. So the row organization that helps with refresh also helps with performance. Okay, so we can skip most of this stuff. So to improve the interface to process further, DRAMs added clocks and are properly called synchronous DRAMs or SDRAMs. To take advantage of SDRAMs is that the use of the clock eliminates the time for the memory and processor to synchronize. So now instead of waiting for some synchronization time, they're already clocked, so they're already synchronized, which is good. The amount of time that we spend doing non-value-added work like synchronization, the less time we spend doing that, the better. So the speed advantage of synchronous DRAM comes from the ability to transfer the bits in a burst without having to specify additional address bits. So instead, the clock transfers the successive bits in a burst. This is called, this is what DDR is. So when we're talking about a double data rate, you can just think of it as instead of transferring a 1 by 1 by 1, we're transferring in bursts now. So this means that data transfers both on the rising and falling edge of the clock. So typically, when we have a clock, we pick a single active edge. So we'll say, we obey a rising edge clock. So that means we'll only do actions on the rising edge. Now double data rate says, okay, well, why don't we just do it on both edges? Pretty good, and it works well in this case. It doesn't work for every case, but for DDR, it does work. So we get a little lucky there, which is good. So sustaining that let's see, so thereby getting twice as much bandwidth as you might expect based on the clock rate. So we're actually accessing data at twice the clock rate, which is good. It's good for the user, especially once data sizes scale, right? So the latest version called DDR4. Is there DDR5? Maybe there is. I don't follow it. I don't work on memory. So a DDR4 3200 DRAM can do 3.2 billion transfers per second, which means it has a 1600 megahertz clock. That's a lot. That's pretty big. It's pretty good. So sustaining that much bandwidth requires clever organization inside the DRAM. So instead of just a faster row buffer, the DRAM can be internally organized to read and write from multiple banks. So just because we have multiple banks doesn't mean that we access them one by one by one. We can play some tricks and we can access multiple at the same time. So that's the idea of parallelism that we've talked about before. So if we can do things in parallel, if we're not using pieces of hardware, well, let's find a way to do it. Let's find a way to use them. Okay. So for example, with 4 banks, there's just one access time, and then accesses rotate between the 4 banks to supply 4 times the bandwidth. The rotating access scheme is called address interleaving. So, we can start working on multiple banks at once. Is there anything else interesting in here? It's sold on DIMMs. That's not really that interesting. Okay. Let's talk about flash now. So flash memory. It's just like the Queen song. Good old Flash Gordon. Okay, so flash memory is a type of electronically erasable programmable read-only memory, or EEPROM. So sometimes EEPROM is also used for so sometimes ROMs are used to hold the bootstrap code for your operating system, but some other times if you want some flexibility to rewrite that bootstrap code, it'll be EEPROM. So unlike disks and DRAM, but like other EEPROM technologies, writes can wear out flash memory bits. That's not good. So how do we cope with such limits? So they have a controller that spreads writes by remapping blocks that have been written many times. So what we're talking about here is if we have, oops, let's get that pencil out. So if we have a grid, we don't want to just pound a single block in this grid with all of our axes because it's going to wear out and we're going to kill that. So what we typically want to do is we want to spread it around. So axis 1 might go here, 2 might go here, 3 might go here, 4 might go here. And so we spread it out evenly. And so this matters even more with things like garbage collection. So when we have to start like moving data around with inside DRAM, it matters even more that we have plenty of cells to work with. So this is called wear leveling. And then we get to the most boring thing. We get to disk memory, the good old magnetic disk. So as figure 5.6 shows, a magnetic hard disk contains a collection of platters which rotate on a spindle from 5400 to 15K revolutions per minute. We have a read-write head arm, or it has a movable arm that has a small electromagnetic coil called a read-write head. So we're physically having to move something now to access data. So if we wonder why it's slow, well, for none of the other technologies, we have to do something physical. We're sending electrical signals. So that's why disks are slow. And there we have here's your arm, and then here's the disk itself. You'll see that these disks are split into regions. We'll probably go over that later. And then you have the read-write head. So those concentric circles are called tracks, and they make up the surface of the disk. I don't know if we're going to go into why they're split into tracks. In the OS course that I'm doing, we'll likely go into something about that. So then we have sectors. So one of the segments that make up a track on a magnetic disk. So a sector is the smallest unit of information that is read or written on a disk. So say if you have your disk and this is your sector, or this is your track, then a sector will be one of these guys. And that's the smallest unit that you'll be able to read or write. Okay, so the disk heads for each surface are connected together and move in conjunction. So basically you have multiple platters and you have multiple arms moving at the same time. So the term cylinder is used to refer to all the tracks under the head at given point on all surfaces. So the time it takes to move the arm from one spot to another, on the disk we call this the seek time. So then once the head has reached the correct track, we must wait for the desired sector to rotate under the read-write head. And so this is called the rotational latency or the rotational delay. So you have to keep in mind that two things are moving here. You have the arm moving across the disk, but the disk is also spinning, so there's no guarantee that we're going to perfectly align the spinning disk and the arm at the exact same moment. So sometimes we'll have to wait, and that's called the rotational latency. And they calculate it here, but it's not too interesting. What's more interesting is getting into the basics of caches. Okay, so in our library example, the desk acted as a cache. So the desk is what we use to put all the books on, where all the information that we were looking for was located. Okay, so cache was the name chosen to represent the level of memory hierarchy between the processor and main memory. So the first commercial computer, boring. So in this section, we begin to look at a very simple cache in which the processor requests are each one word. So 4 bytes, 32 bits. And the blocks are also consist of a single word. So, oops, I don't know how that happened. So they're saying that the smallest unit that we can transfer between different levels of the memory hierarchy, so between memory and between the memory and between the cache and the processor is a block, which is a word in this case. Okay. Readers already familiar with the cache basics may want to skip 5.4, but hey, listen, I don't know if you guys are familiar with caches, so we're going to go through 5.4. So 5.7 figure shows such a simple cache before and after requesting a data item that is not initially in the cache. Before the request, the cache contains a collection of recent references. So the time of the reference is denoted by their subscript. And the processor requests a word xin that is not in the cache. The request results in a miss, and the word xin is brought into the cache. So here we have our different accesses. We notice that x4 does not exist in the cache, but in this case, we actually have open spots. So after we request it, we load xin into the cache, and so it's now in our L1 cache, or if we have just a single cache, it's in our cache. Okay. So in looking at the scenario in 5.7, there are two questions to answer. So how do we know it's in the cache? How do we know if we access x in or x sub in, how do we know that x sub in is in the cache or not in the cache? So that's the first question. And then if it's not in the cache, how do we find it? So the answers are related. If each word can go in exactly one place in the cache, then it's straightforward. To find the word if it's in the cache, the simplest way is to assign the location in the cache for each word in memory is to assign the cache location based on the address of the word in memory. So this cache structure is called direct mapped. So since each memory location is mapped directly to exactly one location in the cache, the typical mappings between addresses and cache locations for direct map caches is usually simple. For example, almost all direct mapped caches use this mapping to find a block. So we'll go into how this looks. So basically we have striated addresses. So in this case, if we have this limited cache size, basically every single, in this case, so this would be, the first one would be 0, 0, 0. Then we're here at 1, and 1 would map to, say, 1 here. But then, we're going to eventually roll over because we have a kind of a small cache here. So we'll see that we'll have striated values, all these gray ones, that all map to a single spot. So we can't fit everything from memory into the cache. It wouldn't make sense that way. Our entire reason behind a cache is we have something small and fast. So we sacrifice this idea that we can't store everything. And in this case, we have a very simple design, so we just put this direct mapping in there, which we'll see can be good, cannot be good. So if the number of entries in the cache is a power of 2, then the modulo can be computed simply by the lower order log 2, so cache size in blocks, bits of the address. So an 8-block cache uses the 3 lowest bits, so the lowest bits 0, 0, 1, to determine where it goes in the cache. So if we have 8 blocks here, all we're going to do is care about those 3. So we're going to in space 1. Over here, this is 5. We look at the lower 3, this is 1. We look at the lower 3, this is 5. And then so on and so forth. 1, 5, 1, 5. So we're only looking at the last 3 bits. So direct map caches, super simple in order to calculate this. Okay. Oops. Let's get the highlighter out. Because each cache location can contain the contents of a number of different memory locations, how do we know whether the data in the cache corresponds to the requested word? So this is the idea of we have multiple things mapping to a single spot in the cache. How do we know that is this the right thing? We answer this question by adding a set of tags to the cache. The tag contains the address information required to identify whether a word in the cache corresponds to the requested word. So we'd like to not have this value and this value both be read if someone accesses spot 1 in the cache. We'd like, if we're requesting this piece of data, if this value is in the cache, we'd like it to not hit and load that to the processor. And so we do that with a tag. So what is a tag? The tag is a field in the table used for a memory hierarchy that contains the address information required to identify whether the associated block in the hierarchy corresponds to the requested word. So 5.8 is going to discuss this. Okay. Well, I guess it doesn't. So for example, in figure 5.8, we need only have the upper 2 of the 5 address bits in the tag, since the lower 3 index field of the address selects the block. So in this case, if we have 5 bits for this address, so let's go ahead and write this out. So if we want to determine if 0, 0, 0, 1, if we want to determine if this is the value that's being stored right here in the cache, the first thing we do is we look at the bottom 3 bits, because that's going to determine our mapping. So we go, okay, so we want this spot in the cache. We want the spot that corresponds to 0, 0, 1. Then we look at these upper bits, and we go, okay, so I have 4 different things mapped to the cache. Which one is it? So it's this one. It's the 0th element. If it was, say, a 1 here, that's a bad 1, then it would be this one. Because if we look at this number right here, which is 0, 1, 0, 0, 1, if we just look at the tag, it corresponds only to this address. So that's how tags work, and that's how addresses work. Okay, and then we need a valid bit, of course. So we also need a way to reorganize the cache block that does not have valid information. So for instance, when a processor starts up, the cache doesn't have any good data. Caches are volatile. That means that they require power in order to retain their values. So once we lose power, we want to say, okay, none of these things are necessarily right. They could be, but we can't guarantee it. So we have to mark it as invalid. So we need to know that the tag should be ignored when it's invalid. So the most common method is to add a valid bit to indicate whether an entry contains a valid address. So what's the big picture when we're talking about this basic knowledge of caches? So caching is perhaps the most important example of the big idea of prediction. It relies on the principle of locality to try and find the desired data. So this idea that we're predicting the values we're going to need next, and we're predicting it based upon the idea of temporal locality. So we're predicting that if we use something, we're probably going to use it again soon. And spatial locality. If we use something in this location, we're probably going to use something that's right next to it. So the hit rates of the cache prediction on modern computers is often above 95%. So we do a good job with this. You can thank all the architects back in the day for pioneering the field and doing this. Okay. So let's see. Below is a sequence of 9 memory references to an empty 8 cache block cache, including the action for each reference. So what do we have here? So it's empty at first, so everything's going to be invalid. So in this case, we'll just look at the we'll look at the first. So let's look at the first one. Let's look at 22. So 22, the address will be 10110. So based upon the scheme that we were working on, we're going to store it in spot 6 in the cache, and it's going to correspond to the second value mapped to that spot. So when we access, and we're going to set some valid bit out here to 1 after we load this in. So initially the valid bit is 0. So when we first access it, it's a miss. Then after we access it with this value, it's going to be set to a 1, and this is going to be our valid bit. Now when we access it again in this third access, we're going to hit this time because the valid bit is now 1. Now let's see where we get. Are they going to show us one that 2 different values to a single location? 0, 1, 1. I'm looking at all the misses right now. I don't even know if they... Oh, it doesn't look like they show a good example of that. That's okay. So in this case, if we had something like 0, 1, 1, 1, 0, so what we would do is first we look at, okay, this is where I look in the cache. So this is the cache slot. Then I check the tag. So did these tags match? So does 1, 0 equal 0, 1? No, it doesn't. So it doesn't matter. This valid bit, we're going to reset to 0 now because we have to bring in. So that it's no longer valid until we bring this in where it becomes valid again, right? So that's the basic idea of how caches work. And they have some pictures on how they do this, but we get the basic idea. And so this is what something like a cache would actually look like. And this is for like the RISC-V 64-bit, so that's why we have a byte offset over here because we work in terms of bytes. So we don't have this sub-byte granularity for accessing, so we just we pad zeros here. And so this will be 52 plus 10, 62, 64, so double word. Double word means 2 words. Words are 32 bits, 64 bits. So in this architecture, the tag is 52 bits. The index is 10 bits. So what we do is we use the index to look at the spot in the cache. That'll give us the index, like we already saw. Then what we do is we check the tag. So we check to see if the tag that we have up here is equal to the tag that we have in the cache. And we make sure that it's both, this is an AND gate, so we make sure that it's both valid and equal. That's what we do here. And if it's valid and equal, we send back that it's a hit, and we access that data. Okay. Okay, this is nothing too interesting. So here we have a quick graph that's on the miss rate versus block size. So note that the miss rate actually goes up if the block size is too large relative to the cache size. So each line represents a cache of different size. Okay. So this is one of the key ideas when we're designing a cache, right? So we want to hit, kind of this sweet spot, this local minimum, right, when it comes to cache sizes. So it turns out that increasing the block size forever won't actually increase or decrease our miss rate anymore, and in fact may actually increase our miss rate. So there's really a sweet spot in a lot of these designs. So let's see. So larger blocks exploit spatial locality to lower miss rates. as figure 5.11 shows, increasing block size usually decreases the miss rate, but the miss rate may go up eventually if the block size becomes a significant fraction of the cache size. So this is because we can't hold multiple different spots of memory in the cache at the same time. So if our cache is, say, this big, and we load in a block and it takes up the entire spot in memory, well, if it's not in this block, we're out of luck. So maybe we're looking at two different spots in memory in a program. So it may be advantageous to have, say, two smaller blocks in there. Then the other problem is we're having to transfer more data. So if we have to transfer larger amounts of data, intuitively it's going to have to take longer. Okay. So how do we handle a cache miss? So we talked a lot about cache hits, but we haven't really talked about what happens on a miss. So before we look at cache in a real system, let's see how the control unit deals with cache misses. So the control unit must detect a miss, and that's by that equality of the valid bit and if the tags match. Okay. So of course, a cache miss, just for review, it's when the requested data cannot be filled because the data is not present in the cache. So modifying the control of the processor to handle a hit is trivial. So misses require a little bit of extra work because now we need to dig down into the memory hierarchy. So the processing of a cache miss creates a pipeline stall. So if it's not there, it's going to take some extra time, so we can't just proceed forward as normal. We have to stall. We have to say, wait, I got to catch my breath. I have to find out where this data is, potentially for a long time. Now, there's a way of getting around this, but not if you're an undergrad taking this course. As far as you know, there's no way to get around it. We have to wait. So for a cache miss, we can stall the entire processor, essentially freezing the contents of the temporary and programmer visible registers and wait for memory. But like we said, more sophisticated out-of-order processors can allow execution of instructions waiting for a cache miss. So basically we find other work to do while we're still waiting for something to come back from the cache. How's everyone doing? Is everyone still doing well here? I'm glad that you're all here today. Okay. So let's see. So let's look more closely at how instruction misses are handled. So let's see. If an instruction access results in a miss, the content of the instruction register is invalid. To get the proper instruction into the cache, we must be able to tell the lower level in memory hierarchy to perform a read. Since a program counter is incremented in the first clock cycle of execution, the address of the instruction that generates an instruction cache miss is equal to the value of the program counter minus 4. So once we have the address, we need to instruct the main memory to perform a read. We wait for the memory to respond, so since the access will take multiple clock cycles, and then write the words containing the desired instruction into the cache. So we can now define the steps to be taken on an instruction cache miss. So we have to take our PC minus 4 because that's the value of the instruction. So we have to send that original value to memory. So we have to say main memory, find it, find where it is. Then write the cache entry after it comes back, after it says, hey, look, I went everywhere, I found where I need to go. Then we have to turn in the valid bit. We have to make sure it's valid. That way when we actually perform the write again, it doesn't kick it out. Because remember, they test that equality, and then they also test to see if it's a valid bit, if the valid bit is set. And then restart the instruction at the execution step, or at the first step, which will refetch the instruction, and this time it'll find it in the cache, which is good for us. So how do we handle writes now? So that's how we handle a read. and also a read miss. So how do we handle a write? So writes work somewhat differently. Suppose on a store instruction, we wrote the data only into the data cache without changing main memory. Then after our write to the cache, memory would have a different value than in the cache. So this is what we call inconsistency. So the simplest way to keep the main memory and cache consistent or coherent. So consistency and coherency are actually two different things. I shouldn't mix those together. So the simplest thing to do is just to do a write through cache. And this says if I write something to the cache, I'll send that write all the way out to memory. It's not going to be done right away, but it'll be on its way. It'll finish at some point. So that's what a write through cache is. So the other key aspect of writes is what occurs on a write miss. So we first must fetch the words of the block from memory. So we have to find it. And that's similar to the read step that we went through last in the last small section. So after the block is fetched and placed in the cache, we overwrite it with the value that we got. We also write the word to main memory using the full address. So if we have a write miss, we have to go to cache, or we have to go to main memory, or maybe even disk. Usually main memory, not disk. We have to go to main memory. We have to pull in the where we're writing to. We overwrite it, and then we send it back to main memory with a write through cache. So it's very simple, but of course it's not good performance. With a write through scheme, every write would cause the data to be written to main memory. We're going to generate a lot of traffic here. So our solution is to use something called a write buffer. A write buffer stores the data while they are waiting to be written to memory. After writing the data into the cache and into the write buffer, the processor can continue execution. When a write to main memory completes, the entry is freed in the write buffer. So now we say if we get a write, the write goes to cache, and then it also goes to this larger structure, which is a write buffer. So this is cache, this is the write buffer, and we'll have multiple writes in here, and then eventually, as they commit and as they finish, they'll free up individual spot by spot by spot. Okay. So the alternative to the this write through scheme, which seems a little funky, is to use something called a write back scheme. So in a write back scheme, when a write occurs, the new value is written only to the block in the cache. So we're not writing it directly to memory every time, we're just writing it to the cache. Okay. So the modified block is written to the lower levels of the hierarchy when it is replaced only. So if we access something that has a same, not the same tag, but the same, if it has the same index in the address, but a different tag, and so we have to evict it from our cache, we have to send it out of the cache and bring something new in, that'll be the only time we write it to main memory. And so we save a lot of times on writes there. Okay. So this is a 16K cache with the intrinsity fast math. Each contains 256 blocks with 16 words per block. Okay, so nothing terribly special here. All we're basically doing is now we have a cache that is a larger size, so instead of holding, say, 64 bits, we're now holding 512 bits. And then each of those 512 bits gets split off into 32-bit chunks, and we have this multiplexer that uses these lower bits to decide which part of this larger structure we're actually accessing from. Okay. So what's a split cache? So we haven't talked about a split cache yet. So a scheme in which a level of the memory hierarchy is composed of two independent caches that operate in parallel to each other, with one handling instructions and one handling data. So this is this idea of having an instruction cache and a data cache. So if we remember from when we talked about the control of the processor and how a pipeline processor functions, we talked about instruction data or instruction memory and data memory. So just like we have instruction memory and data memory, we can have an instruction cache and a data cache. And that way, the program counter is what we're going to use to, index where we're going to be looking at in instruction memory, while in data memory, we're using these other memory addresses that we have. So as a summary, we looked at the simplest of all caches, the direct map cache, with a one-word block. We saw how we can make use of things like spatial locality. And then we saw that in order to avoid performance loss, we can increase the bandwidth of main memory by transferring cache blocks more efficiently. So this is doing schemes like write back caches instead of write through caches. So some interesting things that way. Now, how are we going to improve cache performance? So the first thing we can obviously do is using multi-level caching. And this is the idea where we have a smaller, very fast cache on top, followed by a little bit smaller, a little bit bigger but slower cache underneath it. And this would be something like the L1 cache and then the L2 cache, and so on, all the way until disk, main memory, then disk. Okay. So this is just some calculations and how to calculate cache performance. Cache performance is a fairly simple thing to calculate. You basically just take in, okay, what's my hit rate in the cache? What's my time to access if I get a hit versus my time when I get a miss? And if I get a miss, I need to look at what is my hit rate at the next level of the memory hierarchy, and so on and so forth, depending on how many levels of the memory hierarchy you have. Okay. So let's talk about reducing cache misses with by more flexible placement of blocks. So right now we have this fixed direct map cache, and we'll see that it's pretty inflexible. As it sounds, it's direct mapped. There's no flexibility there. Where you're mapped is where you're mapped. So let's talk about the other extreme of things, which is a fully associative cache. So this says that a block can be placed in any location if the cache is fully associative. So to find a given block in a fully associative cache, all the entries in the cache must be searched. But to make it more practical, we can just search all of these in parallel, with the comparator associated with each cache entry. So these comparators significantly increase the hardware cost because we need one for every single entry in the cache now. So we can strike a balance here, though. On the one hand, we have the inflexible, super easy direct map cache, but on the other side of things, we have the fully associative. What if we only wanted? What if we said that, okay, well, if you're a cache block that's working on this range of addresses, well, what if you can only go in this small subset or this small range? Probably would be a little bit better. And so that's where we get this idea of set associative caches. So in a set associative cache is a cache that has a fixed number of locations, at least 2, where a block can be placed. So instead of a block being only able to be placed in a single location, it can now be placed at 2 or more locations. So like we said here, in a direct map cache, let's pull up the pen here. In a direct map cache, one spot in the data corresponds to a single spot in the cache. Now, over here in a set associative, in this case 2, So this data can correspond to 2 places in the cache. So we only need to search 2 places for that data now. And then in a fully associative, we have to search every place because this block could be anywhere in the cache. Okay. So remember that for a direct map cache, the position of the memory block is given by the block number mod the number of blocks in the cache. So if we had a 32 mod, 16, it would be in the 0 block, right? And then a set associative, it would be 32 mod the number of sets in the cache. So in this case, it would be, say, 4 or something, where we have 4 sets in the cache. And so that means that if we had a cache like this, and so we could say that some block coming in would be only able to go to one of these 4 spots. So that's what I mean by set associative. It has a set of cache entries that it can be in, but it can't be in the entire cache, and it doesn't have to be in one fixed place. Okay. So here we have an 8-block cache configured as a direct map, 2-way set associative, 4-way set associative, and fully associative. So here we have a direct map, which basically, we know exactly where it's going to be because there's this direct mapping. In a 2-way set associative, we now we can now be a little more flexible. So we can now pick one of 2 spots to store our data now instead of just one. But that means we have to search 2 places. In a 4-way set associative, we have 1, 2, 3, 4 per set that we have to search now, but we have some more flexibility. We can move things around. And then finally, in an 8-way set associative, or in this case, because of the cache size, it's a fully associative, we can put a cache block anywhere. It's great, or it seems great for us, right? But in reality, we're going to have a lot of it. The hardware cost is going to be big because we have to search 1, 2, 3, 4, 5, 6, 7, 8. We have to search 8 places now. So we're trading flexibility for hardware cost. So misses and associativity in caches. So assume there are 3 small caches, each consisting of 4 one-word blocks. One cache is fully associative, the second is 2-way, and the third is direct map. Find the number of misses for each cache given the sequence of accesses. So 0, 8, 0, 6, 8. So now we can fill in the cache contents after each reference using a blank entry to mean the block is invalid, colored text to show a new entry added to the cache, and plain text to show an old entry in the cache. So the direct map cache generates 5 misses for 5 accesses. So in this case, because we're of size 4, we have to do a mod 4 on every single one of these addresses because we have 4 spots they could possibly be in. So 0, 8, 0, 6, 8. So 0 is going to, mod 4 is 0. 6 mod 4 is 2. And then 8 mod 4 is 0. So for 0, we're going to get a miss because it hasn't been accessed yet. So we get a miss. 8 tries to access the same spot, but now, even though we're looking at the same spot in the cache, it's the wrong value. So we get another miss. Then we access 0 again. Now 8's in the cache, so we get another miss. 6, there's nothing in the cache originally. We get a miss. 8, we loaded 0 into that spot in the cache previously, so we get another miss. So it's not great for us. It's actually very bad for us. So in the set associative, so in this case, we have the set associative cache has two sets, either 0 or 1, with 2 elements per set. So let's determine to which set each block address maps. So all of these would go to set 0. They're all even addresses, so if we have something even mod 2, it's all going to be 0. So 2 mod 2 is equal to 0, but 3 mod 2 would be equal to 1. You can think of mod being remainder. So if it's an odd number, it'll be remainder 1. If it's an even number, it'll be remainder 0 if we're doing mod 2. So let's see what we have here. So 0 is going to go into set 0. Address 8 is also going to go into set 0. So now we'll have two different things in set 0. When we access 0 again, well, okay. Since we have 2 spots we can store per set, we're not going to evict 0 when we load an 8, so we actually get a hit here. We haven't loaded anything in 6 yet, so unfortunately that's going to miss. So we have to kick something out. So what does it make sense to do? In this case, we're kicking 8 out of the cache. And then when we access 8 again, we just kicked 8 out of the cache. We have to load it back in. So in this case, there you go. We get another miss. So we got a single hit this time. It's a little bit better, but it's still not great. So the fully associative cache, now we have 4 spaces that we can hold in memory. So in our first 2, intuitively, because we've never used the cache before, they're going to be a miss. Now in this case, when we access 0 again, we're going to get a hit now, because that was already loaded into cache. We have 4 spots we can store it in, so we're not going to kick it out. When we load in 6, we've never accessed it before, so we're going to get a miss. And then when we load in 8 again, well, we loaded an 8 up here. We didn't have to kick it out this time, so we get a hit. So we went from a 0% hit rate to a 20% hit rate to now we have a 40% hit rate. So not bad. We got some marginal improvement here. And here's some, this is some quantitative stuff. So they use this fast math processor and the spec CPU 2000 benchmark, and they had these. So that's more just quantitative stuff. Not really theory, so it's not terribly interesting. So, but here's how a 4-way set associative cache would look like. So now what's going to happen is, instead of searching one cache this time, we need to search 4. We can think of this as, these are all sets, but we can think of it as searching 4 mini caches. So what we do is we check to see if it's both valid and the tag match, and we have to send the tag over to every single one of these sets. And then we also have to and then we have to index every single one of these sets at the same spot in parallel. So we've got a bit more overhead here. Now we see, instead of 1 comparator, we have 4. Instead of 1 AND gate now, we have 4. We now have to have not just an AND gate, but we have to have an OR gate as well to see if any of them hit. And then we also have to have this multiplexer to decide whose data are we taking, if it's valid. So that's really how a set associative cache works. So now we get into the interesting case of which block do we replace in a set associative cache. So it's easy with a direct map cache because we only had 1 spot to store data in. Every block mapped to a single spot in the cache. But if it can map to multiple blocks, who do we get rid of? So one of the typical ways to do is least recently used. So we check to see, okay, who hasn't been used in a long time? It's likely that you're not going to be used again. The data that we've used most recently, which has been used, the data we've used most recently, probably going to be reused again. If we haven't used you in a while, we'll kick you out, and if we make a mistake, okay, we'll eat the latency this time. It'll be fine with us. Okay. So Lru replacement is implemented by keeping track of when each element in a set was used relative to the other elements in the set. So for two-way set associative cache, tracking when the two elements were used can be implemented by keeping a single bit in each set and setting the bit to indicate an element whenever that element is referenced. So if it's referenced, you basically just count up and down, and that way you can see, okay, I'm most recent. And if the other guy gets accessed, he goes high and the other guy goes low, and now he goes, okay, now I'm the guy that's most recently used. And so the unlucky guy that has a 0 at the end of the day, he gets the hot potato, he gets kicked out, he has to make the long journey home to main memory. Okay. So how do we reduce the miss penalty? So like we said before, we use this with multi-level caches. So when we're talking about what we can fit in a cache, we generally are talking about what's known as the working set. Whoa, guys, it's why so green? Facecam Sram. Yeah, it is alive, surfing. It's nice to see you today. We started a little bit late because OBS didn't want to work. It's still a little buggy, but we got there today. This camera came in today. I'm very happy with it. Okay. So let's see. So in comparison to a single level cache, the primary cache of a multi-level cache is often smaller. So furthermore, the primary cache may use a smaller block size to go with the smaller cache size, and also to reduce the miss penalty. So when we're talking about a multi-level cache, like I said, we want to talk about it in terms of the working set. So typically, for data that we're using pretty frequently, this all determines about how long data is live. So when we talk about if data is live, it's if data is going to be reused again. So we want small amounts of data to be here in, say, the L1 cache. That way, when we access the memory hierarchy, we can just jump back and forth really, really quickly with these small bits of data. Now, if we have a bit more data that won't quite fit in the L1, well, we don't want to pay too much of a price. So we might eat the penalty of missing in the L1, which isn't bad, and then we'll just go to the L2. So not bad still. And then if we have very large data, a very large amount of data, then we just have to eventually bite the bullet. We have to bite the bullet and we have to say, okay, I have to eat the penalty this time. My data, my working set of all the live elements that I'm going to be using right now, it's too big. I can't fit it in the L1, I can't fit it in the L2. I have to use the main memory. There's nothing we can do. Okay, so let's see. So this is just comparing the number of instructions executed. And they're also talking about things like blocking. So there's some clever tricks that we can do with things called blocking, or a lot of times it's called tiling. And it's where we exploit the structure of the cache to design our algorithm so that it fits completely, say, within the working set of the cache. If we can fit everything in the L1, that's great for us. If we can fit it in the L1 and the L2, and we don't have to go all the way to main memory, we'll take that as well. Okay. That's fine. This is just more stuff on miss rates. We get the idea. So it's now important that we talk about dependability. We haven't talked about it much so far. But with caches and this idea that we have to refresh caches, or not caches, but refresh DRAM, we now bring in this idea of, if we have to refresh something, that means there's a possibility of errors. So we should talk a little bit about dependability in the memory hierarchy. And that's the idea of redundancy. So the first thing we need to do is we need to define failure. So users can see a system alternating between two states of delivered service with respect to the service application. One, service accomplishment, when the service is delivered as specified. So if we do something, if we do a task, then hopefully that task gets done the way we think it will. And then the second is, of course, service interruption, where what happens is different from what we expect. So what is reliability in this context? It's the measure of continuous service accomplishment or the time of failure from a reference point. So there's metrics like mean time to failure or annual failure rate, which is a percentage of devices that we would expect to fail in a year given the mean time to failure. Okay. So we can use things. We can use error correcting codes and double error detecting codes, and we can embed this into how we're storing our data. That way, when we say we read the data again, well, we can check some error correcting code and see if whatever data we read is the data that we're actually trying to read. If a bit didn't flip someplace, if a bit flips, it's a good idea that we have a way to recover from that. If we didn't have a way to recover from that, consider the example of something in your machine. So a bit flipping could be disastrous. So a bit flipping on something that's a protection bit in memory, that could flip from being protected to unprotected, and somebody else could read it. And so there's this idea of row hammer attacks that specifically try to do this. So they try to read, write very close to data that's protected, trying to flip that protection bit. And so that's this idea of using some error detection code to see if something went wrong. And so we won't really go into error detection codes too much, or parity bits. It's not very interesting, but the idea is we use them in computers in order to see if something went wrong, and potentially, depending on what kind of code we're using, to recover from it. Okay. So as part of our last two sections that we're going to go over today, we'll talk a little bit about virtual machines. So there's a couple things we need to think about when we're talking about a virtual environment. And typically with a virtual environment, we're sharing the underlying resources. But what we really want to do is we want to impart the idea that increasing isolation and security is one of our primary concerns. They're also popular because errors in the standard operating system and reliability concerns. We also like cloud computing. Not everyone needs an entire PC. We can share it. And then because processors have gone so fast or so good over the decades, it doesn't really make sense to give everyone a coffee-like giant, super expensive multi-$1,000 chip or something. So we can kind of spread that out over a couple of users. And so a lot of universities do this, where you don't have your little desktop thing anymore. You basically just have a monitor that connects to the network, more or less, and it connects to some hypervisor or thin client thing that's been set up. Okay. So we should talk about virtual memory too. So virtual memory enables so many things, and it relies upon this idea of partially of precise interrupts, but itself is very interesting. So in earlier sections, we saw how caches provide fast access to recently used portions of programs' code and data. Similarly to main memory, can act like a cache for the secondary storage, traditionally as magnetic disk. So this technique is called virtual memory. So we can pretend that things are in main memory even if they're on disk, and that's what this idea of virtual memory. So our two main motivations is to allow efficient and safe sharing of memory among several programs, and to remove the programming burdens of a small, limited amount of main memory. So instead of having to manage all this memory by ourselves like we have to do with GPUs, it's why nobody programs GPUs. Most people don't program GPUs because you have to manage the memory yourself, because it doesn't support a lot of virtual memory features. Because this backup storage that we're talking about resides on the CPU. So now we're talking about a shared memory space between an external device, the GPU, and then the CPU, and that's just something that hasn't been done before. Okay. So of course, to allow multiple virtual machines to share some memory, we must be able to protect the VMs from each other, ensuring that a program can read and write just the portions of main memory that have been assigned to it. So we cannot know which virtual machines will share the memory with other virtual machines when we compile them. In fact, the virtual machines sharing the memory change dynamically while they are running. So because of the dynamic interaction, we would like to compile each program in its own address space. So a separate range of memory locations accessible only to this program. Virtual memory implements this translation of a program's address space to physical addresses. So we have this mapping from now virtual addresses that are kind of up in the air, that all map down to that we have to translate back into, okay, now if I actually want this data, where physically in the memory do I have to look up? So this translation process enforces protection of the program's address space. Unless you're on a GPU, then it does nothing. Or at least on until the most recent GPUs. The most recent GPUs, they do some memory protection. Prior to Volta, nothing. They do absolutely nothing. You can read and write outside your virtual address space, or outside of your assigned address range. Isn't that great? Doesn't that sound great for security? Don't you just want to share a GPU in the cloud now? I'll give you a hint. Amazon doesn't even sell they don't even sell shared GPUs in the cloud because of this. Okay. So now we have this idea of, we have a page of memory. So generally we structure, when we're talking about memory, we put them in sections of 4K. The size is usually 4K for a memory page. And we can just pretend that everything's in memory, even if it's on disk. Now, if we try to access that page that isn't actually in memory, and it's actually on the disk, we get what's known as a page fault. And this means we tried to access something that wasn't actually in memory, even though we thought it was. So with virtual memory, the processor produces a virtual address, which is translated by a combination of hardware and software to a physical address, which can access main memory. So this process is called address mapping or address translation. So when we get a page fault, it occurs when we've accessed a page not present in main memory. And upon a page fault, we generally get what's known as an exception. We handle the exception, which means that we go, hey, the memory's not there. So we say, okay, operating system, take the wheel, grab the memory we need from disk, bring it from disk to memory, restart execution. But the programmer doesn't have to do this. The programmer doesn't have to say, is that in memory? Is that on disk? Do I need to think about this? Nope, the programmer doesn't care. The programmer doesn't care, and that's the biggest thing. We care about programmability. We want people to write code, and we want the operating system, and we want the hardware, and we want all the drivers and stuff. We want to take care of this. We don't want to see this. Let someone else do it. Let the software and hardware do it. So going back over a couple terms, so virtual addresses, an address that corresponds to a location in a virtual space, but then has to be translated to a physical address when accessed. And then this address translation, called address mapping, is how we map these virtual addresses when we try to access physical memory. So here we have things like our virtual addresses, and some of our virtual addresses may even access the same physical addresses, because we'll see that our virtual address space is oftentimes much larger than our, which oftentimes and pretty much always is much larger than our physical address space. Contract them. Doesn't the programmer still care because of performance issues that arise from too many page faults? The programmer does care to some extent. So generally, though, from a programmability standpoint, we expect the hardware and the software to make sure that there isn't too many page faults. If you're talking about high-performance computing code, then you need to be a little more clever. But if you're not doing high-performance computing code, oftentimes what the compiler generates will be good enough, and what executes on the hardware will be good enough. So we still care about the performance issues from too many page faults, but a lot of times that's not going to be an issue. We're not going to expect that if some novice programmer writes some application that it's going to be just riddled with page faults. Okay. So here we have a little bit on the mapping. Here we have a little bit on the mapping from a virtual to a physical address. So we have to change this virtual page number. We have to translate it into the physical page number. And then we have some page offset. That way we can find, and this is just figuring out, where in physical memory this virtual page is. So it's a pretty simple process. So the discussion of, so let's talk about this. I saw segmentation. Segmentation is something that's pretty interesting. And fragmentation is also something that's pretty interesting. So if you ever wonder why, in the operating system thing that we'll go over on Thursday, we might get to, at least some point in that operating systems course I'm doing, we'll probably get to the idea of fragmentation. And if you guys remember back in the day having to run something like a defragger, we'll go over why we used to have to do that back in the day, and then why we don't have to do it anymore. But let's still talk about virtual memory. Okay, so the discussion of virtual memory, let's see this. So if you take it a step further, you want everything to be ready in cache memory, which is why you do something like tiling. So that's high performance computing though. So the general person isn't doing tiling in their application. That's a HPC problem. Generally, you want a ninja programmer. So that's what people that are very good programmers are typically called. They're generally called like coding ninjas. So the discussion of virtual memory in this book focuses on paging, which uses fixed size blocks. There's also a variable size block scheme called segmentation. So in segmentation, an address consists of two parts, a segment number and a segment offset. The segment number is mapped to a physical address, and the offset is added to find the actual physical address. Because the segment can vary in size, a bound check is also needed to make sure that the offset is within the segment. So this is used to for more powerful methods of protection and sharing within an address space. But this is an operating systems concept, and we'll likely look at that in that operating system portion. So then we have the actual one of the most important structures, which is a page table. So a full search of everything is oftentimes infeasible. So in virtual memory systems, we locate pages by using a table that indexes the main memory, often called a page table, and we look within the page table for a PTE, or a page table entry. A page table is indexed by the page number from the virtual address to discover the corresponding physical page number. So each program has its own page table, which maps to the virtual address space of that program to main memory. So in our library analogy, the page table corresponds to a mapping between the book titles and library locations, just as the card catalog may contain entries from books in another library on campus rather than the local library branch. Okay. And so here we have the basic structure of what a page table looks like. So here we have the page table register, which I don't think I covered, so let's go back here. So to indicate the location of the page table memory, most hardware include a register that points to the start of the page table, called the page table register. So that's how we find where the page table is. We have a register that points to it. So here we have the page table register, which points to the page table. We take some virtual page number. That corresponds here to a physical page number. We check to see if it's valid. If it's not valid, that means it's not in memory. It's on disk, so we'll have to do something to fetch it. But we won't cover that here. We'll just immediately bring down the page offset. And then we copy down the physical page number down here in order to calculate the physical address. Vibsy, hey, thanks for following, man. I appreciate it. We're having a wonderful day here today. So this is that idea we're talking about if the page isn't in memory. So if the valid bit is 0, then we get a page fault, meaning that it's not in memory. And this transfer is done with the exception mechanism that we saw in Chapter 4, which was our last chapter, and we'll discuss it again later in this section. So once the operating system gets control, we must find the page in the next level of the hierarchy, which is usually something like flash memory with magnetic disk. So similar to the cache, if we get a miss in the cache, you can think of the page table as a similar process where we miss in the page table and then we have to say go to memory. Or not go to memory, we have to go to the disk. So if we skip down a little bit, so because we don't know ahead of time when a page in memory will be replaced, the operating system usually creates a space on flash memory or disk for all the pages of a process when it creates the process. So this is called the swap space. So if we need to move things in and out in our virtual memory space between memory and disk, we have this dedicated space called the swap space. So here we should see how a page table maps each page in virtual memory to either a page in main memory or a page stored on disk, which is the next level of the hierarchy. So we have if we have this 0, so the valid bit is 0, so it's invalid. All the invalid bits are located on disk storage. So in this case, our swap space would be 3. We have 3 blocks of memory. And then everything in here is valid. Okay. Virtual memory for large virtual addresses, it's not terribly interesting. Neither are really writes. Here's a key architectural feature though. So we want to make this translation fast, right? We don't want our bottleneck to be translating virtual addresses to physical addresses. So in this case, we have something called a TLB, which is a translation look-aside buffer. So the translation look-aside buffer is exactly what it seems like. It's a cache. So accordingly, modern processors include a special cache that keeps track of recently used translations. So this special address translation cache is a translation look-aside buffer. We just call it a TLB. So although it would be more accurate to call it a translation cache because it stores translations, not the data. We're not going to have a cache that's storing a bunch of 4K pages in it. We're just going to store the translation. So the TLB corresponds to that little piece of paper we typically use to record the location of a set of books. So that's back to our library analogy. So RISC-V, so this is a RISC-V book, so we should talk about how this is implemented on a RISC-V machine. Uses 4 levels of tables to translate a 48-bit virtual address into a 40-bit physical address. So rather than needing 64 billion table entries for a single page table, this hierarchical approach just needs a tiny fraction. Each step of the translation uses 9 bits of the virtual address to find the next level table until the upper 36 bits of the virtual address are mapped to the physical address. So basically what happens is if it doesn't fit within the first level, then okay, we go to the next level. If it doesn't fit there, we go to the next level. If it doesn't fit there, we go to the next level, and eventually we have, okay, we do this multi-level translation of this virtual address to find this 4 kilobyte memory page, this 4K memory page. 4K is a very standard size. Most things use 4K. Although there are certain applications where we may want a bigger size than 4K. So if we're talking about, there's been proposed things for GPUs of using things, I think they're called super pages, and they're using pages the size of like 2 megs. And so this is because when you're transferring over PCIe from the CPU to the GPU, well, there's a little bit of cost that you're going to pay for that transfer. So if you can reduce that cost by, say, I'm going to transmit a big hunk of data, that way I don't have to do the arbitration over the PCIe bus every single time, and I just need to say, do it once, transfer 2 megs, and then I'm good. Now generally you want to transfer more than 2 megs, but this time instead of having to transfer it at the granularity of 4K, we're doing it at 2 megs, which is a big improvement. Okay. So this is some other processor's TLB, and that's not terribly important. And then they give a nice flow chart to see what happens. So they have a virtual address, they do a TLB access, they see. Sorry for a dumb question. Hey, there's no dumb questions here. What's a RISC-V machine? So are you familiar with an x86 machine? So that's my next question. So if you're familiar with an x86 machine, so the machines that Intel makes, so an Intel processor is x86 architecture. It's the instructions that it uses. So it's an architecture that's an architecture is defined by the microarchitecture and the instruction set architecture. So Intel processors are typically called x86 architectures. No, it's fine. So you can basically just think of Intel processors use the x86 assembly language, right? So we're talking about processors that don't use x86. They use what's called RISC-V. Yeah, no problem. ARM's a very common one. RISC-V was developed by Berkeley. It's more of an academic one. I don't know if anything actually uses RISC-V. It's a good teaching language, though, because it's a reduced instruction set architecture. Feels good, man. Good explanation. Hey, I hope it was a good explanation. Listen, if I ever give a bad explanation or something, call me out on it. Just stop me. I'd be more than happy to explain. Not a problem. Hey, I'm here for you guys. Okay. So let's talk a little bit about implementing protection with virtual memory. I'm a security guy. A lot of my research is security focused, so this kind of stuff is more interesting to me. So one of the most important functions of virtual memory is to allow sharing of a single main memory of multiple processes with memory protection. So we can have a write access bit in the TLB can protect a page from being written, and without this level of protection, a computer virus would become more widespread. So we can add some bits everywhere to say, you know, who's allowed to write where, who's allowed to write what, or not really what, but who's allowed to write where. And so we can embed this into, you know, all these levels of the memory hierarchy. That way someone can't come in and say, hey, I want to read your cache. Seems like a bad idea. So we don't do that. So we add some protection. Okay. Some stuff on syscalls, but that's something that's an operating system concept, really. And we covered syscalls last time in our operating systems lecture. This is handling page faults and some more stuff on exceptions, but we already went over a lot of this stuff. A common framework for the memory hierarchy. We went over a lot of this. This is just tying what we already went over together. So here's something, though, that we should go over, which is why we actually experience misses. So why do we get a miss in our cache, in our L1 cache, in our L2 cache? So there's really three different things. So one is a compulsory miss, also called a cold start miss. So if we have nothing in the cache, or it's a fresh start of a program, well, we can't hit in the cache. We've never used it before, so there's nothing to hit on. So we get a compulsory miss. The next thing is a capacity miss. So these are cache misses caused when the cache can't contain all the blocks needed during execution of a program. If we have gigs and gigs of data that we're working on, there's no way we can store that in our L1 and L2 cache. So, you know, we don't have the capacity to store it, so this is called a capacity miss. So that means blocks have to be kicked out of our cache hierarchy, and then eventually, sometime later, we've got to bring them back in. So then we have conflict misses. So these occur in a set associative or direct map cache when multiple blocks compete for the same set. So sometimes these can be this can be a really bad thing, and there's even things that have been used to prevent this or prevent them from being so bad. So if we talk about victim caches sometime, that's an idea from this guy from Wisconsin, Madison. His last name's Jopi. They're usually called Jopi victim caches. So basically, for a conflict miss, we're saying, here we have some block of data, but then someone else comes in and say, hey, let's color him a different color. He says, I want this spot now. And so this guy kicks this guy out, and now, you know, the blue guy gets that spot in the cache. And so that's what a conflict miss is. So also called a collision miss, of course, because, well, they're colliding. So here we have it's a pretty interesting graph. Now we have to also consider that caches can be expensive. So we have to strike a balance between this number right here, our cache size. You know, if we just said make the biggest cache possible, well, of course we're going to miss. We're going to reduce our misses by a ton. So we have to look at two different factors. We have to look at, okay, are we using a one-way or two-way or a four-way set associative cache? And then what is our miss rate at each different size? Now, a miss rate of, say, 5% might be good enough. And for a simple design, we might say, maybe a two-way is fine here. Maybe I don't care about a four-way associative cache. Or maybe I can say, I can tolerate a 7% hit rate. I can use a one-way or a direct map cache. So this is something that all depends. It's a cost-benefit analysis you have to do. There is no right answer. It depends on what your target is. If your target is for something affordable, well, you probably don't want to waste a bunch of space on some fully associative cache. If your target is something that's super efficient, well, maybe you do want a more associative cache. Or maybe if you're really trying to get that hit rate down, you want a larger cache that is associative. Okay. So here they're going to get into some finite state machines for controlling how the cache works. I'll probably do a video on this instead, just because it'll take too long. What I really want to get into, since it's getting pretty late here, what we should really get into is the classic pitfalls and fallacies, right? So they also have stuff on the ARM Core A53 and the Intel i7. Okay, let's get into my favorite part, the fallacies and pitfall section. So let's talk about some common mistakes that happen. Let's see if this is going to work if I zoom in. Nope, that's okay. Can I write? Not either. Also, your favorite part, listen, I love it. Hennessy and Patterson, they knew what they were doing when they made the fallacies and pitfalls section. This is like the greatest, this is like the highlights that you really want to understand. This is all the nuance. I can judge people by only claiming fallacies. Okay, so let's get started on this. So, pitfall number 1, ignoring memory system behavior when writing programs or when generating code in a compiler. So just because we have these structures that will help you out, they try to exploit locality, it doesn't mean we can just say, hey, you the system, have a blast. Oftentimes we still get this idea of garbage in, garbage out. So we should try to structure our programs as best we can to a reasonable extent to be friendly to the memory system that we're working on. And this is 100% necessary with GPUs, where we're forced to do this. So let's look at pitfall number 2. So forgetting to account for byte addressing or the cache block size in simulating a cache. So this just goes back to, we need to make sure that however we're supposed to be accessing a cache in reality is what we're simulating. If we're, say, transferring too big of a data size, so a cache block size that's too big, then that might not be realistic, because we may be, we may think that we're doing better or potentially worse than we should be. So a lot of those things determine our output of a simulator, and we work in simulators. When we're designing architecture, as an architect, you're not building these things. You can't. It takes months and years to build these things because you have to lay them out on a transistor level. We use simulators. What's up, my guy? Kasu, how are you doing today? Are you having a wonderful day? It's Monday. It's my favorite day of the week. In fact, every day is my favorite day of the week, as long as you guys are here. Let's see another pitfall. So, pitfall, having less set associativity for a shared cache than the number of cores or threads sharing that cache. So, we want to make sure that we're not thrashing a cache, and that means we want to make sure that we're not just constantly evicting all the data in our cache and never hitting on it. So we want to make sure that if we have a multi-core chip, that everyone isn't pointing to the exact same spot. Because if everyone's pointing to the exact same spot, they're all going to be kicking each other out. And that's bad, as you guys can probably guess. Let's see another pitfall. Extending an address space by adding segments on top of an unsegmented address space. So let's read into this a little bit more. So during the 1970s, many programs grew so large that not all the code and data could be addressed. With just a 16-bit address, so computers were then revised for 32-bit addresses through an unsegmented 32-bit address space called a flat address space, right? By adding 16 bits of segment to, let's see, I lost where it was. So this just goes into this idea that we want to make something that's easy to address. We don't want to make it so non-intuitive by playing around with the address space too much. We want to make it simple. We want to make it easy to use. We don't want to say, by adding segments, we can turn every address into 2 words, one for the segment number and one for the segment offset. If we have registers that only support a single word, well, this is going to cause problems because now we need to find some way to have 2 words that represent a single variable or something, but now they're across 2 different registers. So we want to not extend the address space by adding segments on top of an unsegmented address space. What's a fallacy? Disk failure rates in the field match their specifications. So you see some specs out there, don't believe them. Two recent studies evaluated large collections of disks to check the relationship between the results in the field to specs. So one was of almost 100,000 disks that had quoted a mean time to failure of 1 million to 1.5 million hours, or a annual failure rate of 0.6% to 0.8. So they found that 2% to 4% was actually more common. So this is like 5 times greater than that was on the spec sheet. So if you're looking at a spec sheet to tell you your mean time to failure or how long it's going to last, don't. There's your hot take of the day. So fallacy. Operating systems are the best place to schedule disk accesses. Not always. As mentioned in 5.2, higher-level disk interfaces offer logical block addresses to the host operating system. So the best an OS can do to try and help performance is to sort the logical block addresses into increasing order. However, they don't necessarily know about what the physical pattern on the disk looks like. Oftentimes, that's on some small microcontrollers that are actually on your hard drive itself. So, oftentimes, the OS isn't the best spot. Sometimes it's the disk. Sometimes the disk knows everything about itself, and the operating system doesn't. Let's get another pitfall. Implementing a virtual machine monitor on an instruction set architecture that wasn't designed to be virtualizable. Let's see. So, many architects in the 70s and 80s weren't careful to make sure that all instructions reading or writing information to related hardware resources information were privileged. So, let's see. So, read control registers in user mode that reveal that the guest operating system is running a virtual machine. And then check protection as required by the segmented architecture, but assume that the operating system is running at the highest privilege level. So if we don't have an instruction set that was designed to be virtualizable, we may potentially leak information or cause some other bad things to happen. So we may incidentally allow an out-of-range read or an out-of-range write because we don't know that two things are not supposed to share. And so a lot of architectures now, they provide extensions that support this. Another thing that extensions are provided for is specific encryption and extensions. So there's AES extensions to the x86 instruction set, and the reason why they have that is because they found that people could infer information by timing instructions on x86 processors. So if we can find a way to remove the timing and any information that an attacker could potentially get, that's what we'll do. And so they extend the instruction set, and that's why x86 is a nightmare, because they extended and they extended and they extended. And then some concluding remarks. So we saw the memory system is built upon a hierarchy. We see that we have small fast memory or small fast structures at the top, like L1 caches made out of SRAM. And at the bottom we have slow but large capacity objects like disk or flash. We saw that the entire idea behind caches is really prediction. We predict that we will reuse data. We predict that we'll use data that's close to one another. So things like prefetching, where we speculatively go, okay, well, if you used part of an array, well, you'll likely use the rest of the array. So we'll fetch that from memory. Yeah. That's really the key point of memory. And that's what we have for today. Listen, guys, I had a fun time today. I think we learned a lot about computer architecture. We learned a lot about memory. We talked about what does a cache look like? How do we do things like translation? How do we move from something simple like a direct map cache to a set associative or a full associative cache? What else did we see? We saw how the virtual address space worked. So if we don't want to have everything be physical and physical memory only, if we want to pretend like we have a larger memory space than we do, we can use virtual memory, and we can pretend that we have all of it in memory, even though some's in disk. And we can have a swap space on disk where, as needed, we can swap page in and out of that swap space. We also talked about dependability. So we briefly covered, we can add some error correcting codes to make sure that when we actually have when we have an error in memory or someplace, we can recover from it, and that's very important to us. Then we also talked about some different policies that we can use in order to refresh from our caches. And and the key ideas behind caches. So prefetching and this tiered hierarchy. That's what caches are all about, right? All right, guys. I had a lot of fun today. I want to thank you all for joining me. If you're interested, tomorrow we're going to be talking about compilers. We're on to Chapter 3 of this textbook, Crafting a Compiler with C. We're using the new version. I bought this version a while ago. It's got the super old yellowed out pages and everything. I think this book is from the 90s. I think it's like from 95 or something, or 96. Oof. It's from 91. So Wednesday we do computer networks here, if you want to join us for that. Thursdays are always operating systems. That's always a blast. And then Fridays we do logic design. So if you're new to computer engineering, it'll be a great chance for you to get the fundamentals of computer engineering down. And then Saturdays I reserve mainly for research. So I've got some deadlines coming up, so it'll probably be stuff related to that. So last weekend we did, what did we do last weekend? Oh, we looked at precise exceptions the entire weekend. That was good. We did some write-ups. We read some papers. We read a paper from 1985 by Jim Smith and Andrew Pleskin. We read another paper by that group from Barcelona. And we read another paper by the guys at Wisconsin-Madison. Good group over there. Anyone have anything? Anything else? You guys want the desk tour? We can do the tour of the Nick from Engineering Today desk. Yes, tour please. Wowee. Okay. Let's see if I have anything out here. I don't. So let's go on the brief tour. Let me make sure I don't break anything. So here we have it. Here we have the Engineering Today desk. So up here we have all of our textbooks, starting from algorithms, operating systems, networks, advanced programming in the Unix environment. A personal favorite of mine, the computer architecture book. This one's an NVIDIA GPU book. Pretty good. We have a little vacuum. We have our peanut butter and our emergency copper spoon, just in case. We have numerous pieces of writing equipment, including my personal favorite, our lovely fountain pen. We have a couple notebooks, a good old 3-hole punch. We have our stylish leather mouse pad that was given as a gift. That way we can use our $3 HP mouse on it. And then we have the Shakeology bottle that carries our protein every single day. Our little Wacom drawing tablet. We've got our microphone. We've got our lovely HD 650s, a true favorite. Is this a house tour? This is the Engineering Today lab tour. And then we have, let's see if there's any revealing information anywhere. I don't think so. So then we have the rest of the lab. We have more machines. We have that weird square machine over there. That guy's got an AMD APU in it. We have that guy over there. A lot of fun stuff. And then this is where I work. And then I put a jar of peanut butter on the camera to keep it still. Because that's what we do here at Engineering Today. All right. So thanks, guys, for joining me. We had a lovely time today. Join us tomorrow. We'll go over compilers. It'll be a lot of fun. But until then, I hope you guys learned something. Shiny, eat a cookie. Hey, I think you're pretty cute, too. See you later, guys. We'll play the title on the way out.